Hi, welcome to the Signal Path. In this episode, we're going to take a detailed look at the Analog Discovery Pro. We're going to do a teardown, a whole bunch of different experiments, and we're going to push it to its limit and see what kind of capabilities this particular USB-based instrument has. Now, these USB-based instruments rely heavily on the software that's going to run on the computer, but this has some tricks up its sleeves in terms of the scripting capability and the sophisticated waveform software that governs its operation. So I'm excited to put it into test. Let's take a look at it. So let's take a look at the Analog Discovery Pro, the ADP3450 model, and see what kind of hardware capability it gives you out of the box. Now in the front, we have a 4-channel oscilloscope. This is of course the 4-channel version, and it's nice to see that we have 14-bit converters behind these BNCs. That means that you're going to get very nice dynamic range and some fine resolution in the measurements you're doing, and 14-bit is really quite good for an oscilloscope. Now they're running at 125 megasample per second, and if I guess, I would say that a pair goes into a single ADC, and we will see that when we do a teardown. That means that there are some limitations when two channels are on potentially. Now the 3 dB bandwidth of these channels is about 50 megahertz, and of course there are 1 mega ohm 15 picofarad inputs. There is no 50 ohm option, and that can be an issue if you connect a long BNC to it, so that you go from 50 ohm into high impedance, and even at 50 megahertz you could potentially run into some problems. But with a 1 mega ohm probe, it's going to be no issue at all. This does support half a gigasample per second oversampling, but that's of course for repetitive periodic signals. That's essentially offset sampling, and then you can build a waveform at much higher equivalent sample rate. Having 4 channels is very nice. This is, I think, a must. Essentially nowadays, if you want to do anything serious, you need at least 4 channels. Now on the right side, we have a waveform generator. This is also 14 bits at 125 megasample per second, and most likely coming from a single chip as well. Again, having 14 bits for generating arbitrary waveforms is very, very useful. You will get, again, very good dynamic range from those signals, and we will test that. And these are 50 ohms, of course, coming out, and the analog bandwidth of each channel is about 15 megahertz. Now on the left side is where we have our 16 digital IOs. Now these are bidirectional, so they can do pattern recognition and do digital decoding, I2C, SPI, and all the classic typical things. That's all done in software. You can also program them to be output, and that we use for arbitrary waveform generations of some kinds. These are digital pattern generations that you can program directly into the software. We will take a look at that too. There is 2 ports here, VIO. These are digital IOs that can be configured for digital power supply as well. They go from 1.2 volts to 3.3 volts, 300 milliamps. It's unfortunate that they don't go to 5 volts because all of these IOs are 5 volt tolerant, but you can create 5 volt power supply here. And this is essentially for digital circuitry. It's useful to have it. It would be nice if it went a little bit higher. All of these inputs are also protected for high voltage inputs plus or minus 50 volts internally, so you don't damage something if you accidentally connect it in a weird way. But overall, yep, some basic functionality is included, and of course the software is what's really critical with something like this, because that's how you can do mixed signal measurements, combine different capabilities of different channels, and create some complex measurement capabilities with the software. Now on the side, we have our power button, of course, which is nothing unusual. At the very back, we have 2 triggers. This is very nice to see. You can create some complex trigger conditions using the dual trigger input. There's a whole bunch of USB ports available for external storage as well as Wi-Fi, so you can add your own USB Wi-Fi to it. And there is an Ethernet port standard as well as a USB device. Now, one of the strengths of this instrument is the scripting capability. We'll take a look at that. And if you run a script, it will run natively on the instrument. That's very different than having to run it on a host PC, because the latency between getting the data in and out and synchronizing and so on is eliminated when it's running locally. So that's also something that's included, and the power supply, of course, comes with it as well. So I think we should take this apart now and take a look inside of it and see how it's constructed and see if some of our guesses in terms of its architecture were correct. And once that's done, we'll do some experiments with it. There's a minor complaint I have with what comes with the instrument. Now, you can get this with or without probes, but it always comes with this. And this is the interface to all the digital IOs as well as the built-in power supply that I just talked about. But this is really too short, and it's not a really easy thing to use. I mean, everything terminates into these headers, and it can be useful in some situation, but it would be better if you saw this in a nice longer ribbon that can get you a little bit further away from the instrument and have some label on these so you know exactly what you're dealing with. I mean, they are color coded to some extent, but I think this is such a simple thing to change, and I think the user experience on the digital channels will be vastly improved if this cable were to be a little bit better. So let's take a look and see how this instrument is put together. Now this is a fairly complex board because of the mixed signal nature it has. It has some sensitive analog things like the oscilloscope input. It has analog outputs from arbitrary waveform generators, but it also has a lot of digital activity that needs to be taken care of, going on through, let's say, the FPGA, the Ethernet, the USB controllers, and so on. Now, because they have a lot of space, they've managed to push all of the noisy things to the perimeter of the board, decoupling them from the sensitive analog inputs. And that also, of course, all the DC-DC converters. If you look in the corner here, we have a lot of DC-DC converters by the inductors and capacitors. You can see here some on the right side as well. Some are adjustable, nicely labeled. These will go to the user accessible power supplies. There are also some linear or voltage regulator based ones, and those are allowing you to power things that are sensitive like the DACs and the ADCs, and you don't want those to run from DC-DC converters. So this nicely decouples everything. So now we start from the analog inputs. We have a 4-channel oscilloscope here. Now, just like every other oscilloscope, you have single inputs coming in, and the very first thing they see are some kind of signal conditioning. There's going to be a bunch of relays here, and these relays allow you to switch things like AC coupled, DC coupled, potentially impedance switching, as well as various gain stages. You may want to switch between, let's say, a low gain stage and a high gain stage, and these are done in a hybrid fashion sometimes. Sometimes some of the gain is done with solid state control, and some of the gain is done by attenuation, by doing relay switching in the front end. But the signal coming in still needs to be amplified at some point, especially if it's small. And the very first thing it hits is this component here. This is an analog devices. This is what they call a fast FET op-amp, 1 gigahertz bandwidth, ADA 4817. Now this is going to give us the gain and potentially adjusting it and so on, but it's still a single-ended signal. And if you want to convert it to a differential, you also have to prepare it to drive an ADC. For that, they're using a linear technology LTC6406, that's this component here. It's a 3 gigahertz low noise rail-to-rail input differential amplifier. This allows you to drive the input of the data converter, which is right over here, in a nice differential fashion and get all the benefits that comes from differential signaling. And of course, these ADCs require a differential input for their ultimate performance specs to be met. And this is a dual ADC. You can see barely the traces coming from the two differential inputs. One goes here, one goes here. And this particular one is also an analog devices part. This is an AD, let me see if I can remember the part number, AD9648. This is a 14-bit, 125 megasample per second total data converter. So if you turn on both channels, you're going to get only half of that. But this is a 14-bit converter. That's a lot of data still being generated by each of these data converters. And we have a symmetry over here. On the other side, we have exactly the same thing. We have a slightly different positioning of these relays, which is interesting. But nonetheless, it's exactly the same behavior. We have another identical component. Now, all the data generated by these data converters, that's now 250 megasamples per second, 14-bit in total, has to be routed to something, and of course, eventually makes its way to this FPGA, potentially under the heatsink. And there's some memory associated with that FPGA as well. So that covers this entire portion, which is our oscilloscope input. Now, coexisting with that, we also have this dual channel arbitrary waveform generator on the left side, and that's based on another analog devices component. This is an AD9717, which is a 14-bit, 125 megasample per second dual output that I believe is also half the rate per output. So that's why you get 2 channels of waveform generation. So then the data from that has to come from the FPGA as well. But because all of this data is handled through the FPGA, you can do some clever things. You can synchronize the data capturing and the data generation, and therefore you can do frequency response and impedance measurements, which are some of the capabilities that this instrument has using the software that comes with it, which is quite nice. And of course, all the digital inputs, they're also going to be buffered at some point and then directly controlled by this FPGA. We have a whole bunch of other chipsets over here. These are going to be Ethernet interfaces, USB controllers, nothing really super exciting. These are just the digital IOs and power coming in over here. This has Ethernet and device, so multiple ways of controlling it. Now, I wish this had a Wi-Fi module. Now, Wi-Fi modules in instruments is always a tricky thing because Wi-Fi is obviously radiating, so you're going to have a hard time coupling and isolating it. But at the same time, 2.4 gigahertz is above the frequency of pretty much everything on this board that you're looking at, so with some filtering, I think it's possible. Now, note also, as I mentioned earlier, that there is nothing isolating these input analog channels from each other. There is no cage around them. So even though there is some signal coupling through the board, and that you might be able to handle with some board design, signal coupling from channel to channel just over the air is very hard to block without a cage. So on this early production unit, they didn't have that, and I'll show you what they did to improve it and to make sure that these channels are well isolated from each other. I also want to take this out to see if there's anything on the other side. I don't think so, because most things seem to be accounted for, but let's take a look at it anyway, and then we can look at the modified version. And as we suspected, there's not much else going on in the back. We have potentially some Ethernet chipsets and so on, and then some additional memory near the footprint of the FPGA. But yeah, looks quite simple on the other side. And here is their solution to isolate the channels from each other without having to redo the board again. So without having a new board revision and not throw away a whole bunch of stuff they've already designed. So normally, if you redo the board, you can move things around, create some ground pads, and then you can solder in a shield or clip in a shield between the channels. Now, if you don't want to do that, you can still make the shield like this, find some clever places to bolt it down using some existing screws, and of course missing and not touching any of the components that are there, not shorting them, and then finding a way to ground it. It looks like they're using these copper woven wires to go to the other side of the board where there are some exposed grounds, and then basically clamp it down there, and that way you get grounding on this. Now this is going to get you pretty close to where you would be if you redone the board, but this saves tons of money and tons of redesigned resources, and they can use all the boards they have already and meet the isolation between the channels. So it's a nice, clever design to overcome an initial oversight. So here is our test setup. I have acquired this board here, which generates a variety of analog and digital waveforms. It's a mixed signal board for testing various type of signal imperfections and so on. So we can use this to evaluate the performance of our Analog Discovery Pro here. Now this requires a 5-volt power supply that's coming from a Rohde & Schwarz power supply, because as we said, this guy can only go up to 3.3 volts in his adjustable power supply section. So there's a lot of things we can look here. So let's start first with some AM signal modulation and see if we can detect any problems with it. And of course, I'm always going to be using this board in different experiments so we can see how well this software behaves and how well it can catch various issues from this board. And here we are with the Waveforms software. This is a central platform used by Digilent to control all of their instruments and perform all the different kinds of measurements. It's an impressively rich software. There's so much to do in here. Sometimes the user interface is a little bit difficult to use, but in terms of getting things done, there is really almost no limit to how much stuff is hidden within the capabilities of this software. There's also a very good help built into it, allows you to see not just the architecture of the instrument, but exactly how to use it and how various parts of the waveform software actually works. This is a free software that you can use as long as you have one of their equipment. This is how you would control it. So I've already connected everything up, and we're going to try to create an oscilloscope measurement here. So you can create multiple measurements and they will show up in a tabbed fashion. You can combine them as we will see. So let's try some oscilloscope measurement. Here we go. Here's our scope. You can open it, and as soon as you do that, the instrument will be automatically configured with the 4 channels at the inputs. I've already partially changed the settings and turned off channel 2 and channel 4, which we're not using. Let's go ahead and run this. As soon as you run this, you get the live update, of course. And right now the waveform is jumping all over the place because we don't have the correct trigger. The trigger is set to channel 1, and there's several different trigger types that you can define and conditions for those to be met. Right now it's on automatic triggering, that's why the waveform is moving. Let's go ahead and set this to 2 volts so that we can stop this from jumping around. There it is. So we have 2 signals here. The signal at the top is the synchronization signal. That's synchronized with the AM envelope of the signal. At the bottom is the AM modulation itself. And you can see that it has some envelope and some high frequency AM carrier embedded in it. Now you also, if you look closely, you can see some aliasing artifacts. You can fool the software and push it into corners where it would make a mistake and produce weird artifacts, which are the consequence of aliasing. And the reason is because our sample rate is 5.9 megahertz over here. And the reason is at a 500 microsecond per division, we're capturing 32,768 samples. So the instrument will always keep that buffer full. So depending on what sample rate you put in, it will have to have a certain horizontal divisions. So we can zoom in, for example. You can see that these 2 numbers will move together in order to meet the condition of the number of samples. If you go over here and manually enter it yourself, let's say 125 megasamples per second, you would be then fixed at a certain horizontal division. So let's zoom back out and take a look and see what we can do with this. Let's do some basic measurements. Some measurements, let's say, on the signal at the top. So we can go ahead and open the measurement tab. There's a measurement tab. We can add a whole bunch of measurements to it. Let's say we define some of our own measurements on channel 1. Let's measure the vertical peak to peak. Let's add that. Let's also add the RMS value, for example. Let's close this. Let's go to horizontal. Let's add the frequency so we can see the frequency of the envelope of the AM signal. And let's go ahead and close that. There it is. You can see very nicely and very fast update rate. It is every time it captures a new 32,000 samples, it will update those values as well. We have a 3.6 volt peak-to-peak signal, frequency 2.4 kilohertz. That's our envelope signal. Okay, looks nice. We can go ahead and close that. So if I ever open it again, if I go under measurements again, it will keep those measurements there. You can of course resize this and put it in the corner if you want to. Okay, let's get rid of it for now. Now if I zoom in a little bit, I will notice something interesting. If you look, every once in a while, it looks like there's something going on in the AM signal itself. If I zoom out a little bit more, I'll put this back in the center, you can see it happens here occasionally. It doesn't happen here in the middle, it happens again. So it looks like it skips every other AM envelope. We want to take a look and see if we can capture that a little bit better. Now you can zoom in here and look at it, or you can use the zoom function, which I like quite a bit in this software. Click on zoom. There you go, you get this zoom window, and that's the window on the right side. Now we can make this one larger, and I can move this waveform anywhere I want. Let's center it right over around here, and we can zoom in. There we go, very nice, look at that. So it is very clear that we have a glitch in the AM signal itself. And these are typically, could be hard to find depending on the software. That's why I'm going through it step by step so you can see how the software navigates. Another interesting thing to note is that that glitch causes another tiny glitch in the synchronization signal as well. And the reason is because this glitch has a very high frequency content to it because of the sharp edges. And that couples into the other traces on the PCB. And that tiny variation is caught with the high resolution ADCs that are built into this device. So really quite nice. You can capture that. You can do a single capture, for example. You can stop it. There's our waveform. We can add some markers over here. These markers will give us the frequency of the AM signal quite easily, or we can turn this marker off, turn this one on, and then we can see the exact voltages at different times throughout the signal. I really like how fast and smooth the cursors work on this. I think they've done a fairly good job on that. Let's go and close this. You can see on the right side the histogram of the signals. This is how often the signal is present at a certain amplitude. It's very good. We can actually show it here at the bottom. There it is. So because the edge, for example, the top and the bottom of this waveform flatten out before it comes back, you can see that histogram shows a stronger presence at these ends than in the middle because the slope here is the highest. So all these are quite useful. Similarly, with the AM signal, the histogram has a higher probability in the center of the waveform. So yeah, just a quick overview of how you can move around and navigate on the oscilloscope. I think they've done a pretty good job. So here's a different waveform, and this waveform looks like a simple square wave, but it does have a problem. Every once in a while you can see that it shifts around and something seems to happen to it. Now this event that's happening is actually quite infrequent, but because we have a reasonably fast update rate, we're able to actually catch it. If I zoom out further, we'll be able to see that, yep, indeed something happens every once in a while. And I want to catch this. And if I turn on the persistence will fill up very quickly, showing that there is a trigger point that's shifting around, jumping around, and causing the waveform to overlap in a different place. Okay, no problem. Let's close that. Let's change our trigger type. Instead of looking at the edge trigger, let's look for a pulse that potentially could be a problem with this waveform. Let's turn on the pulse. So we're looking at a positive pulse. Now nothing happened. You can see it's doing exactly what it was doing before, and the length of the pulse is quite long, 1 microsecond. You can see the other side, which is the length of the pulse being shown over here. Now 1 microsecond is a very long time, and that's probably not where the pulse is. Let's make it shorter. Let's bring it down to, let's say, 48 nanosecond. And there you go. As soon as we do that, no problem, we can catch this very infrequent event. Now if I zoom out quite a bit, you don't see this anymore because it doesn't happen very often. Once you catch it, the next time it happens is quite a long time afterwards. Yeah, it's very easy to catch this. Let's go ahead and turn on the persistence on. And there you go. Now with the persistence on, you can wait for as long as you want, and you will not get an overlapping region. So it is quite useful to be able to use this kind of triggering. As you know, in oscilloscopes, these kind of infrequent events are hard to catch, and having fast update rate of this instrument seems to help a lot. So let's take advantage of some of the digital capabilities of this instrument. I have here 8 digital bits that are coming from our board, and I also have a DAC output, both filtered and unfiltered. And we want to look at the correlation between these signals and the cross-triggering capability of the software. So let's go ahead and do some mixed signal measurements. So I have also opened the logic analyzer right next to the oscilloscope, and because these are tabbed and windowed applications, you can essentially order them and arrange them any way you want. In the oscilloscope, we have 2 signals. On channel 1, we're looking at the raw output of a DAC, and on channel 3, we're looking at the filtered version of the same signal. The raw output of the DAC has the very flat regions between the different digital states going into the DAC, and that's what you would expect to see. And of course, once you filter it, those things disappear because they're high frequency content. If I go ahead and enable the histogram, you can clearly see the different flat regions of the raw output DAC being quite obvious in the histogram as well. Now, we're triggering here on channel 1. So if I move the trigger point, of course, you can see that the waveform will shift with it. That's what you would expect to see. On the digital side, we're not triggering on anything. I have the digital selected, but I'm not triggering any of the channels. Let's go ahead and try to change that. Let's trigger on channel D7. There it is. So now everything is locked together. You can see that all of these bits essentially have transitions that are correlated to each other. But this doesn't tell us anything about the correlation between these two domains. Now we can also go ahead and investigate that, because not only can you select the source of your trigger to be digital, you can select it to be any of the other applications that you may have enabled. So if I go ahead and select scope, now these digital bits are actually triggered, correlated to the trigger point on the analog channel. So if I move this up and down, you can see that they move together. This is really convenient, of course, and this is what normally mixed signal oscilloscopes do, allow you to measure correlated points in time with respect to the two domains. Now this is perhaps not as interesting in this case because we want to find out if these bits at the top are actually bits that correspond to the most significant bit of the output of the DAC. In order to find out, we will switch this guy back to the digital, but then we go back to the oscilloscope and switch that one to be the logic. So now you can see we are on the rising edge of bit 0, that's where our trigger is. And right at that point, we have the 0 crossover point of the raw output of the DAC. So indeed, this is the most significant bit. Every time it is high, we're on the upper waveform, and every time it is low, we're on the lower side of the waveform. And that's what we would expect to see, of course, from a DAC. The reason the pink waveform on channel 3 is a little bit phase offset is because the filter has a phase response. So once the filter the output of the DAC, it's going to have some time delay as it propagates through the filter. That's why that is there. So this can be quite handy. You can change that to any of the combinations. You have a whole bunch of triggering capabilities. But the fact that you can trigger across any of the different applications, that includes waveform generations and so on, can be really, really useful when you want to analyze something very complex. Now, of course, once you have access to the digital data, the software can do various triggering on different protocols. So here we have a situation where the DAC is being engaged every once in a while, and it's very hard to catch the individual pulses that are generated. On the left side, you can see these pulses just come and go, and I want to catch the beginning of the pulses in a very repetitive and predictable way. Now, I know that happens when the I2C interface writes to a particular address. So I have defined the I2C on channel 0 and channel 1 of the logic analyzer, and you can actually define the I2C protocol very simply, just like you would do on any logic analyzer, and I've already defined it here. You can see various packets come and go. Now I can change the way the triggering is done, and it's done on a protocol, and since I have the I2C already defined, I can go over here and define how I want the triggering to happen. So I have it set to a read condition where 1 byte of H41, which happens to be the address of the EEPROM for the DAC, is being triggered. So once I do that, the system is going to look for that particular pattern in the I2C data coming in and only trigger at that time. I'm going to press OK. And there we go. We're triggering precisely at that point. And now I can look at the waveform in a much easier way. And of course, the waveform on the oscilloscope is also now settled because we're using the source as the logic to trigger this. So we basically have now again a correlation. But this is quite helpful because this pulse is not common at all. And in fact, you can see on this pulse, we only have 2. And if I go to the next one, we only have 1. So we have a 3, 2, 1 sequence, and we're able to identify whichever one of these we want to trigger on based on the I2C data coming in. So these are typical, but it's nice to see that the waveform software from Digiland implements this in a nice, usable fashion. We can also use the oscilloscope to measure the waveforms coming out of the arbitrary waveform generator, just to show what kind of basic capabilities it has. So I'm running both channels here at the same time, and you can run them in a synchronized fashion. And since all the data is coming from the same memory essentially, you can sync them perfectly and have total phase control between the two channels. This is common for most arbitrary waveform generators that have more than one channel. So therefore I can, for instance, apply an offset phase to channel 2. And if I do that, you can see that the two channels, of course, drift with respect to each other. That's quite convenient, and this is normal. We can also do some interesting visualization. We can do, for instance, an XY measurement, and measure channel 1 versus channel 3, which in this case will be a line since they're exactly on top of each other. But if I apply phase, you can see that I'm able to create this oval shape, which is what you would expect to see if you plot two sinusoids with respect to each other. You can go and close this one. And if you try to exceed the bandwidth, it does give you a warning. So for example, at 10 megahertz, it does give us a bit of a warning that one of the channels has getting close to its bandwidth limitation, which is nice, so you don't make erroneous measurement not knowing what it is you're measuring. Let's go ahead and turn one of these channels off since we don't need it, and see what kind of modulation capabilities we have. So indeed, we can change this from a simple mode to a whole bunch of different types, and I like the functionality built into the waveform generators. So under the modulation, we can do FM, AM modulation of different kinds. We can combine AM and FM on top of each other. So here we have a 1 megahertz carrier frequency with a 100 kilohertz FM modulation directly on top of it. So if I go ahead and turn the FM off, of course, all we'll end up is just a 1 megahertz carrier. We can also look at the FFT of this signal. Press that. There we go. Here's our FFT. Let's go ahead and make some adjustments. So we will stop here at, let's say, 5 megahertz, and we should see our tone right there. Now, because the FFT is calculated on the 32K samples coming in, it is basically subject to how you adjust your timing. So right now we're at 125 megasample per second, and if I go ahead and zoom out, as soon as the rate changes from 125 megahertz to something else, we will have a longer duration to capture, and then we will get more spectral resolution in the FFT. So you'll see it in just a second. There you go. You can see that we get now more spectral resolution. We get finer bins in our FFT. And I don't see much harmonics anywhere, which is a good sign because these harmonics are not compounded. So the nonlinearities of the arbitrary waveform generator and the nonlinearities of the ADC are both being simultaneously shown here. And we have a spurious free dynamic range of about 70 dB, which I'm quite happy with. Again, that's what you would expect from a 14-bit data converter. We can go ahead and now apply our FM modulation, and as soon as we do, we will see the FM tones sitting on both sides, exactly what we would expect. Now you can do some pretty neat things with the visualization as well. So if I close this one and get rid of the FM modulation, the 3D spectrogram can be quite interesting. And let me go ahead and make this window a little bit smaller so that we don't run into this issue. It would be nice if these two windows actually snapped to each other and moved with respect to each other, but they don't actually quite snap. So in this visualization, you can see the frequency content of the signal as a function of time. So we have time on one axis, frequency on the other one, and amplitude on the final axis. So this is a three-dimensional plot. Right now we have a single frequency, so we only have one frequency content across time, and nothing shows up in the rest of this. But as soon as I apply our FM modulation and zoom out so that we can see all the frequency content, you will be able to see our FM tones. There it is. So on this view right here, you're actually looking at the frequency content. This is basically your FFT across time. So yeah, you can do some pretty neat visualization as a result of this. I quite like this, and it runs reasonably well actually. And it runs even better if you do a single capture. You can see how smooth this is. Very nice. I really quite like it. Let's go ahead and run this again. Now if you go back over here, we have a whole bunch of other capabilities in terms of our waveform generation. We can do things like sweep. We can sweep from one frequency to another. Here we're sweeping from 100 kilohertz to 1 megahertz in a 50 microsecond time. And if I go ahead and zoom in a little bit, you can indeed see the sweep happening in 3 dimensions as well, which is quite neat. Now, because we have arbitrary waveform generator and you can do essentially any data and you can sync them between the oscilloscope and the ARB, you can now measure frequency response, of course, and you can do all kind of interesting characteristics of external devices using these two functions. Let's give it a try. So here's the next device under test that I'd like to characterize using the Analog Discovery Pro. This is an audio amplifier. It's based on a vacuum tube. It's actually a combination of a solid-state front end and a vacuum tube driver. It's meant essentially for headphones. It's not a very good amplifier, but nonetheless, we want to characterize not only its frequency and phase response, but also its nonlinear behavior and see what happens when it's driving a load. So the input of it simply comes from one of the waveform generators of the Analog Discovery, and then one of the headphone outputs is terminated into a load that's going to emulate the headphone, and then it's going to go into one of the oscilloscope channels. So let's see what we can get. So I really want to stress this audio amplifier. So on the right side, we have channel 1 of the waveform generator producing a 1 kilohertz tone at a 2 volt amplitude. So this is a 4 volt peak-to-peak signal going into the line in. It's not a typical situation. We want to see what happens to the amplifier. Now on the left side, I'm capturing the same waveform I'm putting into the amplifier. That's on channel 1. And on channel 3, I'm looking at the output of the amplifier once it's already terminated into an appropriate load to emulate, let's say, a pair of headphones. So you can see that the gain of this amplifier is essentially -1. There's a phase inversion, but the amplitude is about the same. Now I can look at the linearity of this amplifier too. Let's try an FFT first. So I'm going to turn the channel 3 off for a second. Now we have to zoom out in order to produce better spectral resolution from the FFT. And I go all the way back, and you can see at this scale we're looking at some small nonlinearities that are now poking out of the noise floor. And this is because the input of the amplifier is also nonlinear. So we can catch that because we have so much dynamic range from the ARP as well as the oscilloscope. If I disconnect it from the amplifier, these tones will actually disappear. It's an interesting thing to note. But let's go and turn this channel off and now turn channel 3 on. And look at how nonlinear that channel actually is. Even though the waveform looked pretty normal, by eye it's very difficult to see THDs that are, let's say, better than 25. So this THD looks like about -25 dBc or so. So I can go ahead and put a marker on it, and we can read the exact values, for example. There you go. So we're looking at here 998 Hertz, which is the frequency coming out, or 2.6 dB volts. And you can see the next one, we're looking at a value of about -30. So you can calculate THD from this very easily. So this is one way to do it, but there is also a spectrum analyzer app that's built into the instrument as well. It's essentially doing the same thing. It's taking FFTs, but it has additional averaging capabilities that emulate the behavior of a spectrum analyzer a little bit more closely. So let's go ahead. I don't want to look at all these other channels. We can just simply look at channel 3. So I configured it already, and you can see we're getting essentially the same kind of result. Now there is something a little bit unusual with the spectrum analyzer. If I go under the channel options, it's forcing me to put the range at 10 volts. If I go to the range of 1 volt, which is what I was using on the spectrum analyzer, I get an overload condition, and then this result is gibberish. But there must be a bug of some kind, because what you want is you want the smallest range possible, and the reason for that is because it affects the noise floor, of course. So this is why I'm not so happy that I have to be at the 10 volt range in order to get a meaningful measurement, because on the oscilloscope FFT it was working fine. So I wonder if that's a bug or something unusual is going on with this application. But nonetheless, you can see that we can very easily measure the THD of this amplifier. And the frequency response of the amplifier is also quite interesting. Now, as I said earlier, because we have full control of the oscilloscope as well as the waveform generator, and we can synchronize them in any way we want, we can measure frequency and phase response. There's a tiny little diagram up here, and a more enlarged version of it in the help that tells you how to connect it. So I have the device under test sitting between the waveform generator as well as channel 3 of the oscilloscope. I'm also plotting channel 1 at the same time, which is just a through, so we can see the baseline. So we're going to run this and see what it tells us. So it tells us that at very low frequencies at about 50 Hertz, the gain of the amplifier is essentially 0 dB. And you can see the phase is -180. And it's interesting that at some point the phase flips over. I think this is just the wrapping around of the phase calculation. And right when we get to around 100 kilohertz or so, we can see we are almost down 7 or 8 dB. So that's normal. You don't want to process 100 kilohertz signals that much anyway, because you can't hear it. So, and there's also some harmonic distortion behavior of this, as some people find a particular type of harmonic distortion of audio amplifiers pleasing to the ear. I'm not an expert on that, but nonetheless, we can measure the frequency response, and it's very nice. And you can see how easy it is to set up something like this. And once you have all of these hardware capabilities, a good software can take the most out of it. So this is a basic measurement. You can have multiple of these at the same time. You can have several device under tests turned on at the same time, because you have multiple waveform generators and multiple oscilloscope channels. You can make this quite sophisticated in how many things you can measure in parallel. So let's now use the impedance analyzer. So the instrument will use a known resistor and an unknown impedance in order to be able to calculate the frequency response of that particular impedance you're looking for, and it will give you all of its characteristics. So for that, we are using the arbitrary waveform generator channel connected to this capacitor over here, and we're using a 1 kilo ohm resistor in series with it. At the same time, we're monitoring the voltage on one side of the capacitor and on the other side of the capacitor. And since we know what the value of this resistor is, we can use some math to figure out exactly the equations that govern the behavior of our device across frequency. Let's go back to the software and see what it tells us. So let's take a look at the impedance analyzer software, and it's quite sophisticated, allowing you to measure a wide range of type of devices. And if you know what kind of device you're testing, then you can set it to that so that you can get more relevant information. Or if you don't know what it is, you can just get basic impedances as a function of phase and amplitude. So we're looking at a capacitor, so I've set it to capacitance here. We're measuring from 100 Hertz to 1 megahertz, and the system measurement block diagram is shown over here again. Very simple. You can do things like compensation for open and close and save all of those if you want much more precise measurements. For now, we can stick to this. And we're exciting it with a 1 volt amplitude, which is also important because if you have nonlinear devices, you would have to control this to make sure exactly what it is you're measuring. That resistor is 1 kilo ohm here. So it's going to run this. Now, at 100 Hertz, the value of the capacitor we get is going to be pretty flat with respect to frequency, because we are so far away from the self-resonance of this particular capacitor, there is no problem in measuring its value. So if I hover over here, you can see that it's reporting the CS to be 476 nanofarad, which is exactly correct. That's what you would want, that's what you expect, and the phase is minus 89.8 degrees. This is a capacitor, of course, 1 over j omega c. And the phase is 90, exactly what you would expect. Now, as the frequency gets higher and higher, at some point, the value of the capacitance shoots way, way up. That's the resonance of this capacitor, and tells us that the self-resonance of this capacitor, the way it is implemented on the breadboard, is around 585 kilohertz. In practice, you want to stay about a factor of 10 away from that so that the value of the capacitance you're measuring is reliable and repeatable and that you can actually use it as a capacitor. Otherwise, it doesn't even behave like a capacitor in the first place. So a software like this combined with the sweeping of the arbitrary waveform generator gives you all of these measurements in a really straightforward way. So I quite like this, and this can be very helpful if you're designing a board. You want to make sure that your device is actually operating as expected. And just for completion, we can measure the 3 dB bandwidth of this amplifier. I have put a marker at low frequencies, and we will bring this other marker until the delta is about minus 3 dB. There it is. So we're looking at a 3 dB frequency of about 50 kilohertz, which is typical for these kind of audio amplifiers. Now I've only just barely scratched the surface with regards to the waveform software. There's a lot you can do and other hidden capabilities, and each of these functionalities has a lot more to offer. Now there's also an IV tracer. That's quite useful because again we have 2 waveform generators. You can create a multi-dimensional plot, and you can excite, for example, the base emitter of a transistor and the collector emitter of a transistor and get its IV characteristic. Can be really handy when you want to analyze a device that you don't fully understand or you want to check its nonlinear behavior across DC. So we'll save this for another time. Now, as I also mentioned, there is a scripting functionality too. Now this opens a whole new set of possibilities because these code runs locally on the machine and not restricted by the interaction between the instrument and host PC. You can write your own code, you can do all kind of analysis on the data that comes from various hardware capabilities of the box. So you have full control over the waveform generators and oscilloscopes and so on. I have some plans for this for a different video, for some binning and some automated testing, so we can leave that for that, but just be aware that this also exists and there's a bunch of documentation available for the API so you can take advantage of it. And there you have it. I hope you enjoyed this detailed review of the Analog Discovery Pro. There are some minor limitations to this instrument, but the software is definitely sophisticated and takes the most out of what this hardware can give us. Of course, you should do your own homework, make sure that this fits your application compared with some of the competition, but I think it does make a compelling product, especially with the scripting capability. If you're interested in that kind of work and you want to explore it further and have something small on your bench you can carry around and do a lot of different measurements on, I think this is a good option. As always, I'll see you in the comment section.